Hey guys, hope you found your way to Module 8. This is when we're going to start using Khan Academy, but we're also going to have some videos here to talk about some important topics and for our check-ins each week. So we are going to, I'm going to start talking about horizontal stretching and shrinking here. You will talk about this in the Khan Academy videos as well. But I feel like this is a really important topic and often difficult for people, so I wanted to kind of reinforce it. So you guys have talked about all kinds of transformations before. You've talked about vertical stretching and shrinking. You've talked about moving things left, right, up, down, flipping over the x-axis or the y-axis. But this is the one we always save for last because it is typically the hardest for people to picture. And it doesn't look like what you would think it would. So let me tell you what I mean by that. Let's work through this. This is on the website if you want to print this and kind of do it along with me, or you can pause and, do it and then turn the video on and do it, or, handwrite it, or however you want to do it. But I think it is beneficial to kind of start this today. Now this is not necessarily trig, obviously. But it will kind of feed into our trig stuff later. So that's why I wanted to go ahead and do this kind of like a warm-up. If we were really in class, this would be like a warm-up on the first day of Module 8. Okay, so first of all, it's asking us to graph f of x equals x squared. I hope that we all know what that looks like. So I'm going to do that here. 0, 0, of course, 1, 1, negative 1, 1, 2, 1, 2, 3, 4. You know the symmetry, you know the shape, you know what this looks like. Okay, so there it is. Great. So it says now consider the function g of x equals f of 2x. So now let's think about what that even looks like, what that even means. If I take the function f, and notice that it doesn't say f of x anymore, it says f of 2x. Well, that means I'm going to take this function f, and instead of the x in both of these, I'm going to make it 2x instead. So that would mean that g of x would look like 2x squared. I'm just substituting the x for the 2x here. And so it says consider the order of operations and produce a table. So think about your order of operations. If I was plugging x values in here, I would be doubling them first and then squaring them. That's what the order of operations would tell me to do. So with that in mind, let's just make a quick table. I'm not going to put too terribly many entries in the table, but I do want to make sure I have a negative, 0, a couple positives, and so on. So if I plug a negative 1 in here, I get negative 2 squared, which we all know is 4. If I put a 0 in, of course I just get 0. If I put a 1 in, I also get 4. If I put a 2 in, I actually get 2 times 2, which is 4. 4 squared, which is 16. So let's plot that and see what it looks like. I have negative 1, 1, 2, 3, 4. 0, 0, of course, stayed the same. I have 1, 4. And I can't even plot 2, 16, but I do know that it would be very high up there. So let's think about what has happened from my original f to now my g. It seems as though it has been squished. And what I'd like for you to think about here is an accordion. And to help you think about an accordion, I'm going to show you a picture of an accordion. So you can think about an accordion and how you can pull it out or you can push it in. And you can think about this graph of f here, and it looks like what I've done is compressed it, pushed it in to make this graph of g. Now, some of you might say that looks like a vertical stretch to me. It looks like I took it this way and stretched it out that way. Well, we're going to talk about that later. It is not exactly the same thing, but we will discuss that in a few minutes. Okay. Hope you enjoyed that prop there. All right, so let's think about what I would call this. What's happening here. I am affecting the x's. I'm doing something to the x values. So I am doing something horizontally. Whenever I think about affecting the x values on a graph, I think about what is happening horizontally to the graph. So this is a horizontal transformation of some kind. And you can clearly see that horizontally it does look like I have compressed it or squished it. I think Khan Academy is going to use, I forget the word they're going to use, but it all means the same thing: compress, shrink. Any of those words would mean the same thing here. So this is what we would call a horizontal compression. This has been horizontally compressed. And again, horizontally because I'm doing something to the x values. So I would call it a horizontal compression. Now, let's think about kind of the opposite of that. And then we'll talk a little bit more about that. Let's think of h of x. Now I'm taking f and I'm multiplying the x's by a half. So now h of x is going to look like 1/2 x squared. Okay, so again, this does seem like something is going to be happening horizontally. I would call this a horizontal transformation. Let's make a look at that table to, I bet you know what it's going to be, but let's look at the table and confirm what we think here. I'm going to put those same x values in here so we can compare directly. If I put a -1 in here, that's really like -1/2 squared, which is 1/4. If I put a 0 in here, I get 0. If I put a 1 in, I get 1/4. If I put a 2 in, I get 1 squared, which is 1. And so I have this. And so let's plot those. If I can do both of those, I'm not going to be able to show the table really, but I will plot those points and you can as well. When I plot -1, 1/4, I can barely even tell because it's so small down here. 0, 0, still consistent. 1, 1/4, and then I have 2, 1. So if I graph that, you can see, oh, think about the accordion again. Not really sure which way it goes. Think about that accordion again. Now I'm stretching it out. It has been stretched. And so I would call this horizontally being stretched, horizontal stretch. This is a stretch. And again, that's because the x values are being messed with. So this is where people get a little confused, especially those memorizers out there. Don't be a memorizer. Think about why this is true. They see the word compressed and they think big number, and that doesn't make sense to them. They see stretched and they see a small number, and that doesn't make sense to them. And in fact, it's the opposite when we're talking about vertical stretching and shrinking. So why is this? Why does this work? If you understand why, then you'll actually remember this in the future, I hope. So I'm going to show you just a little illustration here. It's not perfect, but it's going to hopefully help you make sense of why this is. All right, so let's say we have this gorgeous tree. Isn't that a great tree? And let's say we have this path headed to this tree. And we have a cute little turtle that's walking to the tree. You with me so far? All right. So if we think about the time it takes for this turtle to get to this beautiful shady tree, we could think about the turtle traveling along the path. What if every time the turtle got, we'll say halfway or whatever, got some way down the path, somebody picked up the turtle and moved him back half the distance. And he went on, and this kind of happened for a long time. Well, you can imagine that it's going to take a lot longer for this turtle to walk to this tree. It's going to stretch out the time a little bit if he's constantly being taken back halfway. Versus, what if somebody sees the turtle and says, oh, let's pick him up, walk with him for a little while, and takes him with them quite a ways and lays him down, or whatever the case may be. Then it's going to take him a lot less time because he's doubled right here in a shorter amount of time. So you can think about that as it is with this here. If I'm taking the x value and doubling it, then it's not going to take as long for this graph to happen. It's going to be compressed. just like it's not going to take that turtle as long to walk there. Versus if I multiply my x's by a half before squaring, well, I'm constantly multiplying by a half every time I plug a number, and it's going to take me all day to get this graph done. It's going to stretch it out quite a bit so that the graph takes up a lot more time and a lot more space, a lot more of the x-axis. So just something to think about, why that is the way that it is. So let's turn to the back then and generalize what we just found. Again, you might want to pause and see if you can do this by yourself, because this is kind of like the do you know what just happened sort of page. For a function f of x and a value a, if a is greater than 1, then f of a of x, f of ax is a horizontal, of course, because I'm affecting the x values, and compression, because it is taking less time if I'm doubling or multiplying by 3 or whatever the case may be. So in other words, it gets done much faster. If the function is multiplied by a number between 0 and 1, a fraction, then of course it's still horizontal because I'm multiplying the x's, but it will be a horizontal stretch. It will take a lot longer for things to get done. So how and why is this different from vertical stretching and shrinking? So I just wanted, this is just some algebra here. If I look at my first example over on the other side and I have this, we now know that we're going to call this a horizontal compression, like we understand that. But if I was to multiply this out, distribute this exponent, I'd get 4x squared. Now the way that this is written, this looks like a vertical because I'm taking the entire function and multiplying by a number. This actually looks like a vertical stretch by a factor of 4. So interestingly enough, for a quadratic, a vertical stretch by a factor of 4 is the same as a horizontal compression by a factor of 2. Now that's only true for quadratics, because depending on the parent function here, these numbers, these factors here, of course, would change. But it's interesting because a lot of people kind of think, oh, a horizontal compression by 2 is the same as a vertical stretch by 2. No, that's not true, unless it's a line. But in this case, you can think about their similarities. So just something to keep in mind as you go forward. All right, and then of course, next, just being able to produce graphs now, transformations of graphs without a calculator. Hopefully we see the parent here is x cubed, and hopefully we know what the parent x cubed looks like. And hopefully now we know that this is a horizontal compression of the parent. And so if I want to think about what that would mean, I have, the typical x cubed in my mind. Horizontally compressing it, like that accordion, it's going to squish it in there. If you want to be exact here, of course 0, 0 would be the same. If you want to be exact here, you could plug in a value and see what would happen here. If I plugged in a 1 here, that would actually get me 2 to the 3rd power, which is 8, so I'd be way up there. So that's interesting to think about. If I plug a 1/2 in, that is going to give me 1. Of course, 1 cubed is 1, so that's when I'm going to be here. Ordinarily, it would take me all the way to here to be up here, but now I'm going to be there. So you can kind of see, it's harder to see, certainly on a graph, but you can see that, the compression, especially if you compare it to its parent. And then, of course, this last example, the parent function absolute value of x, which I think we all know. This, of course, is going to be a horizontal stretch. I'm stretching the graph out. So, again, I'm still centered at 0, 0, but it's going to take me all the way to 3 before that is going to be a 1. So you can see how this is kind of stretching that out. And, of course, -3 would work the same way. Stretching that graph out and making it much wider than it was. All right, so now you can work through your first kind of set of problems on Khan Academy. There will be a check-in for Friday/Monday whenever you do look at it. Please view that, do it first, and then use it to check in on your progress there. And then next week you will have kind of a similar thing, just a new set of videos and problems, and definitely some word for me as well on clarifying whatever you see on Khan Academy. Please make sure you are aware of office hours and email. Let me know if you ever have any questions about anything. And I miss you guys. See ya.